Hello, and welcome to the IEEE 1547 Interconnection Standard, Enabler of Technical Innovation and End User Benefit virtual workshop presented by the Alaska Sustainable Energy Conference in partnership with the Alaska Center for Energy and Power. I'm Mari Shirazi, and I'm a research professor at Alaska Center for Energy and Power, also known as ACEP, and I'll be your MC today. I'll start off our day as we get into the technical part of the workshop, I will have my colleague, Charlie Vartanian, join to assist with the MC duties. And thank you for joining us. Just as a little bit of a background, I'm going to give you the overview of the workshop series, purpose, and goals. This spring, ACEP has hosted a series of 4 virtual workshops held at 2 half-day Zoom sessions. Free of charge, leading up to the Alaska Sustainable Energy Conference, which is taken in person from June 3rd to June 5th at the Dena'ina Center in Anchorage, Alaska. The purpose of these workshops is to take a deeper dive into specific topics that are of current relevance to the energy opportunities and challenges facing Alaska today. This workshop is the last workshop in the series. This is also the 4th year that ACEP has hosted these workshops, and we have brought some of the top experts and practitioners together to present at these workshops. Previous topics have included energy and cybersecurity, emerging energy technology, ocean and river energy, nuclear energy in Alaska, low carbon energy transitions, carbon capture and sequestration, and energy storage. All of our previous workshops, and this one as well, have been recorded and are accessible online on the Alaska Sustainable Energy Conference website. We're posting the link in the chat in case you want to revisit any of these topics. There's a lot of terrific and still relevant information. So if you're interested in learning more about these topics from the perspective of what could work in Alaska, please revisit this content. It is actually still very relevant. Okay, now just a little bit of housekeeping. Please introduce yourself in the chat. Let us know your name and the organization that you're from. If you're having any difficulties with audio or trouble viewing the presentation, please chat event support for assistance. During the workshop, all attendees will be muted. Please submit any questions you have in the chat. Our moderators will collect and curate those questions, and they will be asked during the panel discussion following the presentation. The recording of this workshop will be available on the ASEC website at www.alaskasustainableenergy.com, now in the chat. So if you have to step away or you want to rewatch or share a presentation after the fact, you'll be able to do that. Okay, so the first thing we're going to do is we're going to start off with an engagement poll, just to know everybody. You can participate in today's polls from your computer. Go to pollev.com/tote. Well, you can see it there in the chat. We recommend using Google Chrome for the best results. And to participate by phone, this one I'll spell out just in case there are people on the phone. Text TOTTAK216 to the number 22333. You will receive a text message once you've joined the session. Type in send your response, and there's what will pop up on the next screen. Okay, so our first poll. Where are you joining from? You'll see a map. Just drop a pin in the map or a circle where you're from. Okay. It looks like most of our folks from Alaska. We've got a couple people outside Alaska. I think I saw one person from Idaho at least. We got some folks in the Anchorage area mostly. Somebody from Unalaska, somebody from Fairbanks, or a couple from Fairbanks. Okay, great. Okay, so the second question, what industry segment or professional background are you coming from? And we tried to give you some options here: student, practicing engineer, policymaker or government, utility staff / management, researcher / scientist, general public, or other. Oh, that's pretty interesting. Okay, so that's actually pretty, well. Okay, looks like about a third of us are researchers. A third of us are policymakers slash government. That's pretty interesting. And there's the remainder makes up the rest of the third about with utility staff, other, and general public. It's interesting. Cool. Okay, so it just now to start off our day, we are going to have listen to a short hello from Governor Mike Dunleavy. He's recorded some remarks for today's workshop, so let's listen to him.
Hello, I'm Governor Mike Dunleavy. Thanks for joining us for today's workshop on an important topic, how we connect new energy technology to Alaska's electrical grid. Today, we're talking about a national standard, IEEE 1547. It may sound technical, but it plays a big role in helping Alaska keep the lights on while adding new energy sources like solar panels and battery storage. This standard sets the rules for how small energy systems safely and reliably connect to the grid. As Alaska continues to modernize its energy systems, understanding and applying the standard will help us lower costs, improve reliability, and unlock new innovation. So thanks again for being there, and I look forward to seeing you at the Alaska Sustainable Energy Conference in Anchorage, June 3rd through the 5th.
Okay, thanks to Governor Dunleavy for taking the time to introduce the workshop. Now I'm going to turn the workshop MC and over to Charlie Vartanian. He's going to provide us with some insight on what we're going to talk about today.
Thank you, Mari. And I would like to also thank the ASEC workshop organizers, you and Alaska Center for Energy and Power and the IEEE, the side I come from, for putting this workshop together. I want to start with a qualifier or a disclaimer. Day one is going to be deeply technical, covering the IEEE 1547 Distributed Energy Resource Interconnection Standard. I'd say it gets pretty deep, but anyone with a background in AC electrical theory can follow. The content itself is probably about at an undergrad EE level. If you don't have that background, still working through it will prep you well for the next day, which I'll touch on in a moment. But to hit the highlights of day one, we're going to learn about the IEEE standard 1547 for connecting DER with electric utility systems. Distributed energy resources include rotating machine-based resources, including diesels, and inverter-based resources, including PV and energy storage. The 1547 standard covers the minimum performance requirements related to voltage, frequency, and other performance attributes aimed at making sure that as DER are added and connected to utility systems, that grid reliability and safety are preserved. In terms of introducing the 1547 standard, we're going to cover the general requirements and then focus on several performance areas: VAR and voltage control, frequency and voltage ride-through. And then after going over these core performance requirements, the second half of day two after the break, we'll continue the review of the requirements covering the topic of interoperability, which is a new topic added to the last update to 1547. And this interoperability clause covers how the DER communicate for monitoring and control of the asset and locally. We'll hear tomorrow about microgrids, for example, and control is key to designing, standing up, and operating a microgrid. So that's day one. Tomorrow, the conversation will broaden. It's going to step back from the granular engineering and start getting into other issues and other industry efforts, complementary efforts to promote the adoption of newer grid technologies that leverage the advanced performance features of IBR. So day two will step back and cover broader issues that elevate to policy and even consumer interest. Specific topics covered tomorrow will include use of DER with newer technology and in newer applications. So we're going to cover guides that address how 1547 applies to energy storage systems and how it applies to microgrids. And then we're going to hear from other industry perspectives, specifically the Unify Consortium. They're going to touch on how they're advancing technology, innovation, and application. And then we're going to cover a new program to certify field forces that can do field verification on the conformance and compliance of both devices and projects, verify their compliance and conformance with IEEE 1547. The highlight of day 2 will be a panel discussion that'll address how the standards we've discussed and these broader industry efforts can contribute to meeting Alaska's power and energy innovation needs. Do a quick time check. Looking good. But to kick off day 1, I'd like to introduce, we're going to start with the IEEE 1547 background, and that'll be presented by Mr. Mark Sira, the chair of IEEE Standard Committee 21, the IEEE Standards Committee that oversees and manages the 1547 set of standards and related guides. Mark is a senior member of IEEE and is the leader of several standards-making organizations, including SC21. Mark has experience in various industries, including distributed energy systems commissioning, electric controls, and automotive. Mark is a Bachelor ME from GMI, Engineering and Management Institute, now Kettering University, and an MBA from Harvard Business School. Let's welcome Mark. And Mark, I'll hand over the microphone to you. Thank you.
Charlie, I think this is those of you that are participating in this workshop, there's a fantastic set of speakers that should give all levels of technology interest really valuable input. And we look forward to any feedback you have in terms of future requirements or systems. And thank you for participating. That's all I got. Thanks. Thanks, Charlie. I appreciate the introduction. As Charlie mentioned, the committee that myself and many of the other speakers work on is Standards Committee 21, and it's responsible for distributed generation, interoperability, and energy storage. I'd like to kick it off with a discussion on why standards are important. It does provide a consensus view of the industry stakeholders of what the requirements should be and technical guidelines based on the current state of the industry. Importantly, they establish common terminology and frameworks for understanding the different elements of the electric power system, and that results in overall improved quality of installations because the various stakeholders all understand the terminology such as point of connection or anyways. And then standards lead to modularity, which is a really important aspect. I got involved in the electric power industry in the late 90s when I worked at Kohler Power Systems. And prior to the passage of 1547, the electric utilities requirements varied so much, it was very difficult to cost effectively develop a system to connect to the grid. Within 2 years of the passage of the 1547 standards, the requirements became known and the modularity really took place in the industry, and we could go to fly-by-wire modular structures for controls, and the industry really took off by a factor of multiple of 5 revenue in the first 2 years. And then an important aspect of the standard designs have a baseline for performance, and that's particularly important in markets that are developing, and it prevents market spoilage, such as low quality products being introduced into a market, and it enables all people access to the best-in-class technologies. The committee I represent and many of our speakers represent is mentioned in the big box on the left. The areas of standards we're responsible for and develop are the Interconnection series, the 1547 series you'll hear mostly about today, the Smart Grid Interoperability Standard, which is the 2030 series. We also get involved in some of the solar PV standards, which are specifically energy storage for solar PV applications. And we also coordinate and co-sponsor a number of standards with other committees to facilitate the cooperation. And our role is really coordination and to some extent outside the box cross society coordination within the Institute of Electrical and Electronic Engineers. This is a snapshot of the 1547 series. This is not all inclusive, but the base standard that's in force is 1547 2018. That was the standard that's in force today. There was an amendment. And then the highlighted in blue is the current project. That's a revision of 1547 2018 that will be hopefully published in 2026 or 2027. There's an amendment to the interconnection test and verification requirements as well. And a recently published standard 1547.2 is an application guide that goes through specific examples and is a amazingly comprehensive, well-done document that allows you to understand specific situations and educate you in the requirements. 1547.3 is a guide for cybersecurity for DER. 1547.4 is related to island systems, and that's a current active working group. And 1547.9 was published in 2022, which is a guide for energy storage system interconnection. It included requirements for bidirectional power flow for storage, which can be a source and a load, as well as unique interoperability requirements for energy storage systems. And then 1547.10 is a recommended practice for DER gateway platforms, which will be a way for utility requirements to be met through an interface with either legacy platforms or other new DER. The 2030 interoperability series, we're not going to talk extensively during this workshop, but I wanted to make sure you were aware of this. The 2030-2011 is the base standard. It's a guide and provides a listing of terminology and definitions for the electric power systems. That's also going through a revision currently. The other next row highlighted in blue is IEEE 2030.5, which is describes a protocol used for connecting and interoperability in California and is currently widely used by the industry. And the bottom row highlighted in blue was passed in 2023. Was headed up by the Indian Standards Board, but it's a safety standard for small electric power devices that are meant to be in a household, nominally 700 watts to 1.3 kilowatts, and allows some set level of standards and safety for situations where you might need a light bulb and a small appliance and a fan as your load. But those are for systems that are not connected to electric distribution system. This is a map in the US, and highlighting the dark green states is where IEEE 1547 has been completely adopted. There's work in process with the state of Michigan and ongoing with the light green states. As we move forward, I did mention there's a revision underway. We're trying to modify and keep the standards up to date and current with the market needs and the technology. What some of the technology changes listed in the middle row are things like grid forming inverters, interoperability requirements, naming new entities and technical requirements, and cybersecurity. I'm just going to move forward. This is a graphic, which I know you can't read, but it is a visual of how we track these standards projects and time the revisions of standards, looking out about 10 years. And the process we use is continually going through update, so we can reduce the time cycle between the required 10-year revision of new industry standards. In summary, my introduction, just wanted to highlight the many changes underway. The 1547 revision, we intended to remove the technical barriers that may exist for grid forming inverters. The addition of some reference for technical requirements for 50 hertz markets. And in the future, we may add more requirements for features that grid forming inverters can perform, and discuss islanded operation and black start. The 1547.4 is an active project that deals with microgrids and islanded systems. 2800 series of standards is for inverter-based systems connecting at transmission voltage. And 2030 interoperability of electric power systems is a revision that will include an updated reference to cyber physical system, cybersecurity, and a more current view of the electric power system and its stakeholders and entities. That's where I'd like to hand this off to Charlie. Is that appropriate?
Thanks, Mark. When you stop sharing, I'll pick it up. Before you leave, I'd like to thank Mark. He actually broke away from a water and energy conference in Washington, D.C. to kick us off. I'll continue with covering the background on 1547.
Thank you, Charlie.
It'll lead into getting into the specifics.
Thank you very much. And thank you all for attending.
Most participants, regardless of where you're coming at this topic from, what industry segment, are familiar that the legacy power system was really built on a model of large central station power transmitted to local distribution substations that further transform voltage down and distribute ultimately to distributions to end users. And at the time, the power flow in terms of the power and energy utilized was unidirectional, one way from central station power. Very little power come from end users. Now, Alaska had a bit of a head start, because you have wasn't quite this. Maybe the rail belt reflects this a bit. But many Alaska systems were built as distributed systems with multiple diesels and power flow going throughout the distribution to meet need as resources come on and off and loads come on and off. But that being said, what is new to both to Alaska and the broader industry is the abundance of newer resources that have really emerged over the last couple decades and really gaining increased traction now. PV coming in really now reaching commercial parity and large deployments. Wind farms, obviously, not present as much at distribution, but I'd say Alaska is actually a location, Kodiak comes to mind, where you will see megawatt scale wind in a distributed setting, plug-in cars, EVs, energy storage. And I think an interesting asset is energy storage coupled with PV, which is the number one form of project in the interconnection queues within the bulk power systems on the mainland. So we have new technologies, a lot of it out of the distribution system. 1547 baselines, minimum, I'll call it good grid behavior. And I think an increasingly important aspect is getting a consistent baseline for interoperability that Jamie will go on into detail later. Energy Policy Act of 2005 required consideration of this standard, 1547. At the time, IEEE 1547 2003, that was the first published standard, for considerations. Since then, all state PUCs and utility commissions cite and reference 1547 as the performance basis for retail interconnection. What that really did is, as Mark noted, it set a common standard for performance across the country, whereas before it was very balkanized with 3,000 plus utilities able to set individual standards. I'd say the utilities had a big hand in coming together to create the first 1547 to come up with a common baseline of what minimum performance could they accept. And then 1547 continued to be cited, both federal and more increasingly state level. There are many state clean energy programs, other incentive programs that require the use of equipment compliant with IEEE 1547 and the related certification, UL certification, that I'll touch on in a moment. Really useful background. What it is, it's a technical standard setting the functional, how a device will function, translated into specific performance, measurable performance metrics around voltage, power level, ampacity. It's technology neutral. So sometimes 1547 is assumed to cover inverter-based resources. No, any. It's rotating machine or inverter-based. Broadly, it should be sufficient for most installations. A challenge in Alaska is the grid performance in terms of voltage and frequency variation can go outside the ranges called out in 1547. So we'll have some discussion about that later. It doesn't make 1547 not usable, but sometimes local markets have to, the various stakeholders have to get together. Hawaii Rule 14 is a great example. California Rule 21 for high renewable penetration are examples where these communities have gotten together and extended some of the ranges to be appropriate for their markets. It's not a design handbook, and one aspect today, no one's going to leave here with a working knowledge of how to design a system to be 1547 compliant. It is not used to establish interconnection agreements. An interconnection agreement may refer to 1547, but in and of itself, it is not an agreement. And it's not prescriptive. It doesn't tell you how to meet the performance requirements. It tells you what the performance requirement is, and it's up to the project designers, the manufacturers, the integrators, the owners, operators, to come up with their own methods to actually implement the systems that meet the performance requirements. So this is from the document itself. The blue are changes that were made in the last update in 2018. A key item, again, is adding minimum interoperability requirements to this standard. And they broaden the system, electric power system interfaces. And a key term within 1547 that isn't necessarily common usage is, you'll see reference to area energy EPS, electric power system. Generally, that's going to translate to your receiving utility. For distribution resources, your distribution or retail utility. I'll pause here so you can scan through the stated scope and purpose. The graphic is useful to highlight that it doesn't delve into design performance of the electric power system, nor does it get into the in-plant performance. It's the performance right at the interface, how that system behaves as received, as seen, as measured by the grid. It took quite a while. So from 2003 to 2018, there was a massive increase in primarily renewable resources. And with the real increase in renewable resources, offsetting and taking a lot of the energy load, not necessarily the firm capacity load, the needs of the grid started changing. So 1547 originally came out as a do no harm standard. If you followed the requirements, there was some confidence that you would not degrade the reliability of the grid. For example, the voltage control requirements were of 1547-2003 was unity power factor, i.e. the DER was not to interact with the grid for the purposes of maintaining local or area voltage. The world's different now. And we'll hear tomorrow from some technology leaders. Technology is different now and very well able to have these devices, DER, PV, energy storage, V2G cars, doing some grid supportive capabilities, like support local voltage, to ride through brief disturbances to make sure that the frequency and voltage deviations are limited, such that load or resources don't have to drop off. So that scale is the balancing in 2018. The 2018 version is being revised now, but not as dramatically as between the 2003 and the 2018. Jeanette, who's up next, will delve into those biggest changes in the 2018 revision. This touches on where is 1547 used. IEEE, through its volunteers, write the content in 1547, but it really doesn't come into practice until someone refers to it, requires it by reference. Another term for 1547 world is authority having jurisdiction. An authority having jurisdiction, for example, can be a state PUC, Public Utility Commission, can approve interconnection rules and tariffs that will typically reference it. More closer to 1547, the UL has a certification that will test and certify that devices and systems, products essentially, are 1547 compliant. Where this comes up most in practice is the certification inverters to UL 1741. And NEC does cite and call out UL 1741 as well. I'll pause there. If any questions come up via chat, just let me know. We could address it. If not, I'll keep going on. What I want to touch on here, Mark had said that the IEEE requirement is 10 years. Now, it took longer than that to revise 1547, 2003 to 2018. But the goal is to get this renewal cycle down to 4 years or less, mainly because not just the technology, but how distributed resource technology is used is rapidly changing. So the pace of change in industry, I'd argue, is well ahead of, well, it is. I think arguably the fact is the pace of change in technology and the use of it on the grid is ahead of that 10-year cycle. And I'd say 4 years is even pretty long, especially at the moment. Another exciting area as we get grid interactive loads, for example, loads that could be dispatched, loads that could change their power regulative to frequency. That could be a real tool, let's say, to help maintain reliability of Alaska small grids. That's an area that's not present in 1547, but is an industry practice that should be considered. And there are those proponents who are arguing to have 1547 look at some level, some segment of grid interactive loads as an example of an industry practice and need, not in 1547, that does warrant some consideration. So this is a little bit dated, but these were some of the drivers for 1547 originally. And that will always continue to be requirements to cease to energize galvanic separation without separation means, without an actual physical switch separating that PV system, that vehicle to grid from the grid. The fear is if the grid goes down, there is a chance that the system could be in a configuration that would allow a DER to backfeed through the transformer at the location and energize the utility's distribution. And if the utility thinks the system is down, but if DER is backfeeding it, that can be a safety hazard. So a core aspect of 1547, the original one, the revision, and going forward, perceivable future going forward, there'll always be a foundational aspect of maintaining anti-islanding. I.e., you don't want unintentional islanding of DER backfeeding and energizing the grid. A new stress is the need to have these assets ride through brief disturbances to continue to support the grid versus tripping off. So there's that tension, and it's an engineering challenge that people do solve that balance the need to not backfeed a down grid, but also don't trip too quick and continue to support the grid through brief disturbances. As distribution systems get more automated, challenges are coordinating with DER. That last bullet ties back to the first two. I'll do a quick time check on myself.
Running a little bit ahead of schedule, so what we're going to do is you can take your time, and we will probably, Jeanette will probably join us at 9:20. So we'll have a few minutes if people have other questions or you have other material you want to cover, or we can take a break.
And Jeanette has probably the media section, so if she started 5 minutes early, that wouldn't hurt. You'll hear the term smart inverter thrown around quite a bit. Let's step back and generalize to smart DER, smart distributed energy resources. An interesting industry practice that I believe falls in this area is self-healing systems, localized black start and recovery, and accelerating the pickup and carrying of load during grid disturbances. On the mainland, a big driver in some very interesting projects around public safety power shutoffs. Really, they're most prevalent in California, but I know other areas, including my own here in the Pacific Northwest, as forest fires get more frequent and more extreme, a bulk power system practice is to de-energize transmission, because smoke will cause relaying of transmission lines and unplanned outages. So they'll preemptively de-energize, also for fire safety risk during high wind. So there's a lot of work to stand up localized microgrids that, for example, carry community centers, government centers, police departments, hospitals, community safety centers. My personal opinion, and doing a little bit of work with Cordova Electric, who you hear from tomorrow, is this ability to black start, stand up, have DER carry some amount of load continually is important to Alaska, and actually Alaska has some thought leaders and some of the best experience. So there's always the balance of safe and reliable, balance against cost effective. So standards that you always need to balance. You don't want to be a barrier to industry interest needs, either a technical or a commercial barrier by making standards too stringent. So I'd say that's why standards development is a continuous dynamic activity, and the 1547 working group, and more broadly, all IEEE standards that are formalized as ANSI standards actually have minimum requirements to make sure we have balanced working groups and balloting pools. So we have representatives of manufacturers, utilities, even some consumer interests, usually through regulatory staff participation. Many times you'll have this national lab community, and you'll hear from some that have led some of the groups writing new standards. The point being, you got to get all these various people in play and engaged to find that middle ground. This is always a challenge too. How do you verify? So 1547 has a standard 1547.1. 1547 base standard gives the requirements for testing. Again, it's non-prescriptive. It just broadly tells what should be tested, what ties the performance requirements to tests. The actual test procedures are actually called out in 1547.1. We'll hear about that tomorrow a bit from Wayne Steck. And UL 1741, which is the certification that inverter manufacturers can certify to, uses that 1547.1. UL applies that 1547.1 in their certification testing. Again, there's a real crossover between 1547 set of standards and the regulatory community. It doesn't have to be just state regulators. Utilities in their procurement specifications can call out 1547. A system integrator, when they go out to their suppliers, manufacturers, can call out 1547 and the related UL 1741 certification. So it is handy for setting that baseline, even at the project level, for what are the minimum performance requirements and what are, for example, you can draw on the testing certification to come up with a commissioning plan. Jeanette is going to talk on some of the key parts of the revision that'll be relevant to Alaska. It ties back to this whole black start and islanding aspect. I hope we're within 2 years now. This slide's a little bit dated. 26-27 is a time frame where 2018 will have the new revision. Again, what you will hear about today is largely not going to change. What you're going to hear about today are the most dramatic changes that happened between 2003, 2018 that set the stage to access and use the smart DER or smart inverter capabilities that exist today. We'll hear from a smart inverter expert tomorrow, speaking on behalf of Google's inverter company. Google's academic partner will be talking about some of these new smart inverter technologies tomorrow. Here's the URL. This is aimed at those who work within the standards development community, but I do want to recommend whether you're a student engineer, interested party, utility engineer, anyone can sign up as an interested party to a working group. You do have to be an electrical engineer, IEEE member to be on the working group, with a few exceptions, but anyone can sign up as an interested party. For those engineers, I've worked on 1547 since before the 2003 publication up to its current revision, from a junior engineer to an old fart engineer at whatever career stage you're at. There's a need for your input and a need for your participation, and it's a great career development outlet. And if you're lucky, it aligns directly with your work assignments and work responsibilities. Here's some citing some documents that give more background. NRECA, which is active and elective National Rural Electric Cooperative Association, has written great papers on 1547. And then EPRI has useful white papers, in particular on some of the newer topics on interoperability, how you come up with your local requirements. One aspect of the revision is there are a lot more decisions needed that are going to have to be made at the local region, among the local consumers and the regulators and utilities. EPRI has very good white papers on that. Well, on behalf of Mark, the chair of SC21, and me and all his various IEEE volunteers, I'm going to go ahead and sign off. Mari, since we do have a few minutes, would love to hear some of your initial thoughts, especially in context of what if 1547 is relevant to Alaska today, and where may it have to go to be relevant to Alaska tomorrow?
I think
on the spot.
Yeah, I think that right now we'll talk more about this tomorrow. Jeanette actually is here and ready to go, but so right now I really like the phrase that it's a baseline for performance. And so as we are specifying these inverter-based resources, understanding, like what is typically expected of them and what can they do and what we should expect from them is really important. I think we'll get into more of the grid forming discussion tomorrow, but that is going to be really important for many of these remote systems. So, but
Thank you.
Janet's here. I will let you introduce her, and I will step back again.
Great. Well, Jeanette is going to be covering the 1547-2018's updated DER performance requirements. Jeanette is a longtime contributor to 1547 standards development and its overseeing committee, Standards Committee 21. Jeanette is currently a protection, operations, and planning engineer at Portland General Electric. I thought you'd be CEO by now, but maybe that's next year. Her focus at Portland General Electric is on DER interconnection, wildfire mitigation, and distribution automation. Please welcome Jeanette. We're honored to have you join us today.
All right. So I'm going to talk about the performance requirements as defined in IEEE 1547-2018. If you've looked at the 1547 over the years, we went from, in 2003, a lovely 27-page document with exactly 6 clauses. It was easy to flip through, find exactly what you're looking for. Well, in 2018, we went up to 11 clauses, 7 new annexes, so it's a bit of a bigger document. So I'm going to talk a little bit about what's in Clause 1, and then I'm really going to focus on what's in Clause 5 and 6. Jamie's going to talk about Clause 10 later today. So, 1.4 talks about general requirements, remarks, and limitations. So the first thing that we did was we removed the 10 MVA MW limit from the previous version. And we continued that this is not applicable to interconnections on the transmission or network sub-transmission resources. The important thing is this is the performance of the DER, not the design of the DER. It's specifying the capabilities and functions, but not the utilization of the DER. So the DER can do all this stuff. It's up to the area EPS or the authority governing interconnection resources, the AGR, to decide what you're going to use. Does not address the planning, designing, operating, or maintaining the area EPS that has the DER. Emergency and standby DER are exempt from certain requirements, such as ride-through, the interoperability, and the communications. And then for synchronous generators, greater than 10 MVA, we use the things such as the IEEE C50 standards that are for synchronous machines. So we're giving precedence to the existing standards on synchronous machines. So getting into Clause 5, which is the reactive power and voltage regulation. So if you're familiar with IEEE 1547-2003, everything was set at unity power factor, which is not ideal. As penetration comes up, that can cause problems. If you have a DER on its own transformer with load, that can cause problems. So this is a good thing. So first thing we had to do was come up with performance categories to define what the DER with voltage regulation does. The category A is the minimum performance categories needed for EPS voltage regulation and reasonable by all DER technologies. Category B covers all the requirements of Category A, and specifies the supplemental capabilities to aggregate to adequately integrate DER into the area EPS, especially when the penetration gets higher or the DER power is subject to frequent large variations. 2018 just has the two categories. What we're working on in the revision to 2018 is category C, which is for energy storage. And that is so that it can have reactive power on both the charging and the discharging side. And it can apply, you have category C applying category A or category B based on the storage technology. But that is coming and might be of interest when that revision is done. So the DER is required to be able to produce or absorb reactive power. When it hits 5% of its rated power, it has to be able to deal with reactive power. There are minimum injection and absorption capabilities, as shown in the table, and the active power output should not constrain the reactive power injection or absorption up to this capability. All of the reactive power requirements can operate within the limits of Table 7. So there are 4 voltage and reactive power control modes. As I stated, they do not operate outside the reactive power capabilities as specified in 5.2. And so these are mutually exclusive. The constant power factor, the voltage reactive power known as volt var, the active power reactive power, which is watt var, and the constant reactive power. The 5th mode is actually a active power mode, the volt watt, which can run with any of the reactive power control functions. So getting into what these reactive power modes are is that under constant power factor mode, DER operates as a constant power factor. It's going to be specified by the area EPS operator, shall not require reactive power exceeding the reactive capability. The power factor settings can be adjusted locally or remotely as specified. And the DER has to maintain the constant power factor in under 10 seconds. So volt var, you can see this is a piecewise limited curve, where you have the injecting, you have the absorbing, you have the deadband, and this is all settable. So you can adjust this curve as needed, as shown in this chart. You have your lower limits, you have your upper limits. And so the good news is that there's default settings for both Cat A and Cat B, but there's also a range of allowable settings so that if for some reason you need to adjust it, you can. The watt var has a similar looking curve to the watt var, but this point it's looking at reactive power and real power to run the village. And this is, once more, it's 10 seconds to respond, less than 10 seconds to respond. And you can adjust the curve through the settings. There are default settings with a range, and Cat A and Cat B are actually default to the same. Constant reactive power capability. The DER operates at a constant power factor specified by the ARPS and doesn't require the reactive power exceeding the reactive capability requirements. And they can be adjusted, and the DER has to maintain it within 10 seconds. So, volt watt. It's a slightly different piecewise linear curve. And so it can also be adjusted. And as I stated, is that the volt watt can remain active while any of the voltage reactive power modes are enabled. To give you an example of that, here at PGE, our default settings for inverters that we don't study is that they have volt var as the reactive power mode, and then they have volt watt also enabled. So we can have both of those enabled at the same time. So as we stated earlier, is that these are defined capabilities, but the performance is at the utility's discretion. And it is up to the area EPS and the AJAR to determine if it's going to be enabled or disabled and how to properly operate it. Okay, I think I will stop. And are there any questions on voltage regulation?
Hey, Jeanette.
Yes.
Maybe I'm not supposed to ask questions, but I'm very interested, and I think it could be relevant for people to hear. Can you talk a little bit more about the volt watt functionality and why PGE is using both volt var and volt watt?
So they kind of complement each other, and having that capability there, because the volt var is looking at voltage and reactive power, and the volt watt is looking at voltage and the power itself. So you get a different response, and with the nature of our system, we felt it was a good match to use both of them, because sometimes one of them was going to perform a little bit better than the other one. Plus, our inverters, in the state of Oregon, we skipped, well, I'll get in this right through, but we basically said all rotating machines are Cat A and all inverters are Cat B, or performance category B. So we know that all our inverters can do this.
It's also now in 18 required. You should be able to have volt var and volt watt, and you can decide whether you want to enable or not.
Yes.
Great, thank you.
Okay. So moving on to clause 6, the response to area EPS abnormal conditions. So what we're going to talk about is the normal and abnormal performance categories, the response to abnormal conditions, the voltage and frequency trip, the write-through capabilities, and the default values and ranges of allowable settings for all of that. So, right through is really a response to the potential for widespread DER tripping. System frequency is defined by balance between load and generation. It is similar across an entire interconnection. So I'm in WEC, so the frequency across WEC is the same. And so one, big frequency deviation could start dumping all of the DER on the system, and that could start causing problems in a number of places, including here at Portland General Electric. So that's not good. And because this impacts the DER, all the DER, whether it's high penetration or it's just, low penetration, it can all come off. The other piece of it is that where we're really interconnected, transmission faults can result in a wide area voltage depression. And if the DER is set too sensitive or, set at defaults, depending on how large and how long that depression is, you can start dumping DER, which will aggravate that event on the transmission system. So we really don't want to do that. So it's really about maintaining a balance between grid safety and the bulk system reliability. So we have tripping requirements and we have ride-through requirements in 1547-2018. Ride-through, really important. It's not a setting. It's not part of protection. It is a capability, performance capability of the DER. Language includes it shall ride through for at least so many seconds. It is the minimum DER robustness to withstand the voltage and frequency disturbances. It may or may not be utilized. It can be exceeded. So there are trip thresholds and clearing times are maximal operational settings. So it shall trip in so many seconds. There are default settings. There are adjustable settings over a range of allowable settings. It's designed such that the ranges that are allowed do not allow for DER tripping to compromise bulk system reliability. One note, and this happens more down here than you probably have up there, is that there are regional reliability coordinators in certain parts of the country that may require settings that lead to utility-specific practices that don't necessarily align with 1547-2018. And that's something to be careful of. So, coming back to the general tripping and reclose coordination. DER must trip for any faults on the circuit was connected, except for the faults that can't be detected by the AREPS protection. The other note is that you can use sequential tripping if needed. DER must detect and cease to energize for an open phase condition directly at the reference point of applicability within 2 seconds. That has not changed. So the reclosing against DER is always a bit of a battle. There is, decisions the AREPS has to make with the DER on the system. And this is, if there's low DER penetration, you don't do anything. As your penetration increases, you might install line VT and do some hotline blocking. You might do some transfer trip. You might look at the anti-islanding and see if it's going to operate faster than your open interval in the reclose on the reclosing. So there's options that the AREPS can implement to mitigate the impact of DER on its reclosing scheme. Okay, so just as we had on voltage regulation, on write-through we have performance categories. And this is really because we are technology neutral in 1547, and not all DER can meet the full extent of write-through that's required to coordinate with the bulk power system. The synchronous generators can't do LRVT. Other rotating machines, energy sources can also have potential issues. So the solution is we have disturbance performance categories. The authority governing interconnection requirements decides on the performance category met by each DR type and application. You need to look, the technical criteria is going to look at the type, the capacity, the future penetration, the type of grid configuration. The AGR may limit the cumulative capability allowed to meet lower level requirements. Non-technical stuff is not the purview of IEEE standards. So that's not really there. And if you're wondering, I will get into what we did. And so it's really important to think about the fact that you need to future-proof this a little bit, is that you may want to actually make sure your inverters can all meet the higher category versus the lower category, just to make it a little future-proof, because you're not going to be able to really change that in the future. So we have normal and operating and abnormal operating performance categories. So in voltage regulation, and then write-through. So write-through, we have category 1, category 3. So in category 3, we have a range of allowable settings, but we also have default parameters. And so this is something that between the DER vendors, the EHRs, and the area EPS, you need to look at. And just to give you a reference is we, in the state of Oregon, all our inverters are category B on voltage regulation and category 3 for write-through. All our rotating machines are category A for voltage regulation and category 1 for write-through. One note, actually, I'll get to this one. So, category 1 is the essential bulk system needs and is reasonably achievable by all DER technology. Category 2 is full coordination with bulk power systems. And category 3 is write-through design for distribution support as well as the bulk system. So this is going to, category 2 is going to help you with the bulk system. Category 3 is going to help things on your distribution system along with your bulk system. We are in the revision. We are working on a category 4, which is for islanded systems, which I think will also be of great interest. Hawaii has had great input on that as they run islanded systems too. But those are the categories. So looking at the terminology that we have for the write-through performance. So write-through, the ability to withstand the voltage or frequency disturbances. So that's right here. Permissive operation, the DER can continue to operate, or it can cease to energize as discretion. You have mandatory operation. You have momentary cessation. Momentary cessation is cessation of inundation of the stage of disturbance with rapid recovery when voltage or frequency return to the defined range. So if it's in momentary cessation, it can quickly go to restore output if it does not go to cease to energize. So restore output is the return to normal. Trip is the full cessation of output without immediate return to service. It's not necessarily a discussion, but return to service is the re-entry of DER to service following a trip equivalent to startup of the DER. So if it does trip, it has to wait for everything to return and be there for a while, and then it can come back. So talking a little bit of cease to energize, it refers to a point of connection of the individual DER units. It means that there's no active power delivery. There are limitations to the reactive power exchange. It does not necessarily mean physical disconnection, and it can be used for either momentary cessation or trip. So looking at the structure of voltage ride-through. So if we look at category 1 versus category 2, you can see that the overvoltage permissive is pretty much the same. The continuous operation looks the same. But as you look at the under voltage ride-through, category 2 goes a little deeper. The permissive operation goes a little deeper. And then you can see the shall trip ranges, where the solid lines are the default settings and the dotted lines are what you can adjust to. So category 3, if you remember what category 2 looks like, mandatory operation is bigger on the under voltage, and you introduce momentary sensation, which requires a fairly long zero voltage ride-through requirement. And the one thing is that if the DER is in momentary cessation and the feeder is faulted and tripped at the station, it will not energize the islanded feeder. It will eventually trip off if grid voltage does not return.
Jeanette, but before we leave the mandatory operation, am I correct in my recollection that green a continuous operation aligns with ANSI C84?
I believe so, yes.
And, having done a bit of engineering support in Alaska, one challenge is their continuous operating range can go outside of C84. The question is, with this future Category 4, will they be opening up some of the ranges to account for the fact that voltage and frequency on very weak islanded systems may be outside of yes, traditional metrics like ANSI C84?
I believe so, yes.
Thank you.
So looking at Category 2 in a little more detail is you have the mandatory operation, the momentary sensation, the permissive operation, and you can see these solid lines are where the default trips are. The dotted lines are where you can adjust a little bit, but any of the timing and the pickups. But so there's the ride-through is the trip settings are coordinated with the ride-through, so they will not impede the ride-through. So restore output after the ride-through performance. DER must hit 80% of the pre-disturbance active current within within 0.4 of a second. It applies when the voltage returns to mandatory operating or continuous operating ranges. So when the voltage comes back up to a good point, it's got that 0.4 of a second to get back up to 80%. It does not have to be steady power. It can oscillate if it's positively damped. And if it does provide dynamic reactive power support, which is not mandatory, dynamic support must continue for 5 seconds before returning to pre-disturbance reactive control mode. So, looking at frequency, trip, and ride-through. As I discussed earlier, it's an interconnection wide parameter. Under frequency tripping needs to be coordinated with under frequency load shedding. And we have a wide range of must trip settings to accommodate small isolated grids. There are no performance categories for frequency. They worked really hard to make sure that both the trips and the ride through were within these prescribed load shedding across the coordinating councils in North America. So if we look at frequency ride through, we have a continuous operation range, we have a couple mandatory operation range, we have some permissive, and we have the trip range. So it's very similar to how the voltage ride through works, but there's no categorization on this. So frequency support. All DER is required to provide droop response for overfrequency. Cat 2 and Cat 3 DER have to provide droop response for underfrequency if power is available. There's only a functional capability requirement. Once more, using this is up to the AJAR or the area EPS. It has adjustable deadbands and droops. And there are response time requirements. So this can be fairly slow to operate because it is droop. Other conditions DR must ride through. There are Rokoff rate of change of frequency requirements based on the category. So if you look at category 3, it can go up to 3 hertz per second change of frequency and have to ride through it. There are voltage phase jump requirements, and there are voltage unbalance requirements. If there's recurring disturbances, there's stuff in the standard about that. So there is a concern about ride-through versus island detection. There's enough voltage trips, both under voltage, under frequency trips. Distribution faults can depress the voltage that on the phase that the fault is on. So you will get some DER tripping, and then you mess up the generation load balance, which will prevent the island from sustaining. There's still a requirement for DER to detect and cease to energize within 2 seconds. For all load generation to load conditions. And then there is an option to extend islanding to coordinate with the feeder reclosing. And what we have seen is that there's really no material increase of islanding risk due to the ride-through requirements as specified by the standard. And there is an in-rail report on multi-inverter anti-islanding with ride-through. So, there are some utilities that use screens and stuff, looking at the protection, the anti-islanding, the hosting capacity, and the fact that we still don't have the best models for looking at advanced DER and running through everything that does on it. And there's time associated with doing these studies. And so, you know, interconnection screening looks at the DER integrations such as protection coordination, reclosing coordination, and risk of islanding. You know, so you have a lot of them, you know, we can pretty much wave them through. They meet all the requirements. They're small enough that they don't cause a problem. If you use fast reclosing, and I can tell you I'm at a company that uses very fast reclosing on our first shot, we do a lot of hotline blocking, just so that we can make sure the feeder is dead before we close that breaker back in. And so you have you can run into something, your coordination for high impedance faults, which means, you know, you're going to be looking at the DER overcurrent protection, the voltage supervised overcurrent protection. And then you have cases where the effectiveness of anti-island detection is suspect. And that is the end.
Jeanette, we have a lot of time. I would like to back up to one concept and get your thoughts.
Okay.
The 2018 revision added the whole concept and the metrics around cease to energize. A key aspect of cease to energize is the asset is still parallel to the grid, but not injecting real power for a defined duration. Just determine, is the grid going to go black or is it going to continue operating? I added a link to the Blue Cut Fire event report where the bulk power operators were surprised to see the DER remained off a minimum of 5 minutes. So if you can go into it, I'm also curious how your utility deals with the return to service. The original 2003 by default had a 5 minute. So if you trip, and here's the key thing, if a DER asset trips, it must monitor voltage and frequency for 5 minutes before it can be reconnected. Now, in a small system, depending on DER, like in Alaska, 5 minutes is a long time. So if you can touch on kind of interested in your operational experience. Are you allowing accelerated return to service? Are you seeing cease to energize actually as a useful tool as penetration comes up in your own system?
So we have not had any problems with the 5-minute return to service. If anything, it's actually been to our advantage on some things. We are allowing cease to energize. Partially because we do see voltage depressions due to transmission tripping because we are heavy into BPA territory and whether it's one of their lines tripping or it's one of our lines tripping, we can see a voltage incursion that could cause some issues with the DER. So we have not seen any problems with cease to energize.
Mm-hmm.
But I also have not had any of my big stuff come in with this yet.
As in bigger DER projects.
Yes.
What capacity range are you seeing, even though they're called distributed energy resources? Are you
So,
breaking the
so
10 megawatt project size?
I have some tens on the system. I have some tens coming in. My average size that I honestly deal with is about 2.99 megawatts right now.
Great. That's probably parallels some of the work in Alaska. If any of the Alaska folks know, I am curious the percentage of load carried by rail belt utilities versus the true, the isolated village types. It'd be interesting to see the rail belts brief disturbance profiles. I know they have a large battery at Golden Valley Electric that has some voltage, momentary sag, swell mitigation capability. And I do think there's even a plan to expand that battery system in part because it buffers load from brief and extended outages on the grid. Um,
And
the other
I will say we had a 5 megawatt battery down in the Salem area that we used to mitigate some BPA switching that could really swing the system without us using that battery.
The other good news, and for the Alaska folks, keep in your hip pocket the speed of response of even just sort of the most general, not customized inverter-based energy storage system is fast enough that find out your utility's under frequency load shedding time window. These systems can respond quick enough to start addressing both frequency. Well, this would be a frequency issue, address frequency dips before the utility's relay settings for under frequency load shedding would kick in, and they'd start dropping blocks of load. For your own under frequency load shedding, how big blocks of load do you drop? Is it substation or even multiple substations at a time?
We do it at the feeder level.
Okay.
So we won't even clear an entire station. We will clear specific feeders. Um, we are in discussions about, if we run across feeder that's becoming high penetration that has load shedding on it, do we want to talk to planning about moving that load shedding to a different feeder? Um, we
Oh, that
haven't run into that yet, but we know it's coming.
wow, that's a customer friendly approach. I work for a large utility that we dropped multiple substations as our minimum block. The only place we did feeder specific was on Catalina Island. Um, I don't know if they even use under frequency load shedding much. I'm going to hold you for one more question and then see if there are audience questions. In my experience, high renewable penetration, typically PV, the first challenge that can cause, let's say, a hold, a stop on more interconnection is utilities problems managing voltage regulation.
And that's where the introduction of voltage regulation is huge. Like I said, we've got some 10 megawatt PV installations out on feeders on the east side of our system. And they all came in under the Unity power factor um idea. We've had to adjust the power factor on all three of them. Two of them we've had to add voltage regulators near them to help with the high voltage that results. Versus I leveraged doing the 1547 2018 with another developer in the hopes that we can avoid adding a voltage regulator to a high penetration feeder.
This is a great example where DER can actually bring a solution that works on both sides of the meter, so to speak. But there are regulatory commercial barriers that have to be overcome. Now, I worked for a utility where at Solar Noon on suburban feeders where everyone's at work or gone and PV is at maximum output, we were getting voltage lift to the point that, yes, we had to stop adding PV. And we didn't use voltage regulators, so and our line tap changers. But here's an interesting idea in Alaska. Solar noon could go for many, many hours during the summer. So I would imagine there could even be more drivers to make sure that they're leveraging, accessing, and using the voltage VAR controllability.
Yes.
To make sure that you don't inadvertently run into a barrier to adding more PV. And again, VARs don't move. So if you've got a voltage VAR problem, they tend to be localized and you're not going to fix it at the system level. So that's our utility was running into the case feeder by feeder. Could be telling people, look, we can't take any more PV. And at local level, they might have been at 20%, but the system was well under 3% penetration. But localized, you will run into problems before you have collective system-wide operating challenge.
We have to use the voltage regulation because we have a feeder. We have I think we have 12 megawatts of solar on it right now. And we have another like 7 that want to come on it, and we're kind of saying we're gonna have to put you on another feeder. Like we just we've hit our limit.
Do you limit energy storage yet?
No.
Okay.
I just actually reviewed a couple 10s out of the same substation. I won't talk about what we're asking them to do in order to do it, but yeah, we have a sorted energy storage. There's a 1720 megawatt just down the street from me that we interconnected on our system.
And to shift gears, I don't think you can see the comments. We've got one here. What caused the limit on adding more PV due to the feeder you mentioned?
It's really the capacity that we can put on the feeder. And I think I forget if we're at 12 or 15 megawatts, but we've already run 795 on the feeder. and
Right.
we're hitting the limit of the capability of the feeder.
Yeah, that's an important point. So when you have all this reverse flow because there's no load and all the PV's on, you could just outright reach the ampacity limit of the circuitry or components. I've seen that. The other problem where I've seen, surprise, need to limit PV is on some systems, you'll get a bunch of single phase systems and you could trigger imbalance such that if you have a 4-wire system, your neutral return will hit its limit. And I've seen that happen. Again, these are so phase balance becomes an issue. Now here's to jump ahead. There are advanced 3-phase energy storage systems that could do interphase balancing, lift these limits. Other limits I've seen, again, you put out voltage regulators. Some utilities won't do that, but they'll hit a limit of holding ANSI C84, primarily because of this issue of PV voltage lift that can happen at solar noon. And they don't have, I worked at a utility that only had switch capacitors and intended to raise voltage during high load. We had no tools to lower voltage because of all these PV. So these are just, some real world examples of what has caused limits. And I do want to highlight, I've seen it over and over, the PV or the voltage management on the utility side being sort of the canary in the coal mine. That's the first sign that you really have to relook at system operations before you could take more PV. In the case of Hawaii, and I know we have some NREL folks, Mari might have been there. I know they worked heavily to help Maui, maybe Lanai. Hawaii aggressively wanted more PV, but their first problem was voltage problems. One solution they found was requiring energy storage to go out with PV as an interim fix and sort of locally manage their PV, which could manage, in your case, that a capacity overload. Oh, hey, here's another question that you're our expert. You can answer. Are harmonics addressed in 1547?
Yes. There's an entire section on power quality that includes a section on harmonics.
Do you require anything beyond IEEE 517? Is that the right standard for harmonic limitations?
No, for the most part, we do not. Our relays can our transformer relays can actually measure harmonics. So if we start seeing stuff, we will investigate. Because we've seen some weird stuff for non-inverter stuff. Just some of our semiconductor manufacturing has had some weird stuff go on.
Within 1547, I think a good news is we don't add anything beyond 517. So if someone's already building, designing to that, they're not going to get caught by surprise
Correct.
by anything in 1547.
Yeah, I wanted to follow a little bit more on this.
I'm 519. Sorry, Marco. IEEE 519.
I was wondering that. Okay, so in this case, this feeder was pretty easy. It was an ampacity limit, but you talked about interconnection studies. This is maybe a little bit outside scope of 1547, but I think people would be really interested. Can you talk about what kind of studies you do at the feeder level? Like, do you get down into EMT studies, or is it case by case?
We're not really here at PGE. We do our planning engineers do a SIME study of the feeder. We haven't gotten so much into EMT yet. I admit I'm a protection engineer, so I'm looking at loading and some stuff like that and what I have at the substation and making some recommendations out the feeder for protection. But we tend to use SIME. We As I mentioned, we are a high user of hotline blocking. All of our new switchgear comes with the line VTs already installed. We do employ transfer trip. And this is where I will do the plug for IEEE 1547.2.
Wait, can you remind us what that one is?
That is the application guide for IEEE 1547 2018. It's IEEE 1547.2 2023. There's a lot of really good information in there. And some wonderful protection guidance. But I will say IEEE 1547.7, which is the System Impact Study Guide. The old version is available, and we are currently working on a revision to that.
Thank you.
Barry, I sent a comment. I think this is an opportunity for R&D to help the utility industry. So Jeanette, I'm a retired transmission planner who used to run interconnection studies. The utility world at best is using dynamic simulation, using equivalent, second order models, highly equivalized. There is no sort of discrete analysis like EMTP, except for very specialized cases. Now, part of the problem is the analytic loading on both the data, sometimes the computational power. You need a real-time, like an RTDS capable system. But I know some of your former lab colleagues are working on these interesting co-simulation packages that can take what the utility may use for static load flow through some limited time series simulation, and then fill in the gaps to move it into a truly detailed EMTP, electromagnetic transients program. But I think for utilities, a lot of it is throughput. They're so overwhelmed with DER studies that if they were to set up and run, there's no time and resources. Now, I do think EMTP on a spot case, some questions can't be answered without that. You need the discrete three-phase switching of these devices and really see the three-phase response of the grid. So there'll be future challenges, future operations that will need that. But I'd love to be challenged on that. Are there anyone seeing the utilities moving more aggressive into EMTP? I'd love to see that. My experience, that is, I'll call it, we'll put the glass half full, an opportunity.
So if people, we still have a few more minutes, so people, throw your questions in the chat if you want. I don't know if we have the capability maybe for people to raise their hand and speak. Monica or Carla could tell us that, but we sort of have this opportunity to pick Jeanette's brain, and so if nobody else chimes in, I'll just ask another one. But I'm going to wait here for a second.
Mark, someone commented on the solar noon shifting 50 minutes in interior Alaska. Is that because the Earth is starting to shift on its axis?
Rich, can you want to type in? Rich, if you want to speak up, raise your hand. And it sounds like Monica would let you speak if you want to talk a little bit more about that.
I will say we can have our peak solar anywhere between noon and 2 p.m. It varies on our cloud cover and whatnot, that it can honestly peak anywhere between noon and 2.
Well, while we're waiting for shy people, I know Rich is not shy, so I'm surprised. Okay, I have this question about the requirement that DER, okay, so there's write-through requirements, but there's also a requirement that it must trip upon detection of a short circuit fault. How does 1547 define that? Like, is it a voltage level or?
It doesn't completely define that. It's a difficult thing to define.
I was just wondering if there would be cases where that could be problematic, for example, in a really small system where you could have like a really low sag for a while and you don't necessarily want it to trip. And yet if it was 1547 compliant, it would, but since it's not really defined what short circuit trip
So,
is.
and I think though is that that's where write through comes in, is that if it's low, but it's not dead, then it's gonna write through. And if it goes dead, then it will trip, but if it comes back, it will just restore output.
Yep, this touches on a tension between island systems and the bulk grid. Jeanette, way back when, part of the argument for having confidence you're actually responding to a short circuit is, for extreme, even detectable deep dips at the project level, it indicates there's a bolted fault somewhere. If you're getting down to 0.2 per unit voltage, there's something big going on. On smaller systems, especially things like ground-related faults, on weak systems, you can't necessarily depend on a 0.8, 0.9 per unit voltage drop to tell you, okay, there's something major wrong. And so, again, the R&D opportunity, I'd say there are people worried about the cost of this complexity. There are highly wired protection schemes. They're looking at zero sequence, other stuff, real time, to feed into protection versus just the time over current, time voltage deviation.
Okay, Rich did reply. He can't talk right now. He said it's shifted due to the Earth's tilt and the sun angle at high latitude. So we're right.
No alien activity is suspected. That's reassuring. Thank you.
It does sound like Jamie is here, but I'm going to actually get one last little question in since we have you here. And that is, can you give us, you already gave us a little bit of a hint about the revisions expected in 2018, like addition of another category, which will be really interesting to us, a performance category, category 4. You mentioned also a potential another category with respect to voltage regulation, I believe, a category C. What other kinds of changes are upcoming that could be relevant for these islanded systems, do you think?
So those are the big performance things. I do know we're playing a little bit in interoperability, just improving that. But I think the the big things are those introductions of the new categories that's going to impact you the most.
Great. Thank you so much for your talk and for spending extra time to answer so many left field questions. Greatly appreciate it. Welcome back. Thank you for joining us. Thank you again for joining us today. If you're just joining us now, we're getting back to our discussion of the IEEE 1547-2018 standard. So far, we've heard from Mark Sira and Charlie Bartanian, providing some background on the standard, motivation and background development. And then Jeanette Sandberg presented in detail some of the updated performance requirements and stayed extra for some Q&A. Okay, I'm going to kick it back to Charlie, who's going to introduce our next speaker.
Thank you, Mari. Very happy to welcome Jamie. So to continue our program, Jamie Cohen will now cover interoperability requirements of 5047 and probably take a step back and touch on a couple interoperability points that are relevant. Jamie is a senior power systems engineer at the Pacific Northwest National Laboratory, working in the field of grid architecture, primarily on system integration and grid edge interoperability. He's responsible for research in the areas of distributed energy technology, power systems communications, protection, control, energy storage, transportation electrification, and distributed control solutions. It's a large portfolio, Jamie. Jamie is the administrator of the GridWise Architecture Council, which is a team of industry leaders who are shaping the architectural principles of an intelligent and interactive electric system. To the audience, if you have questions for our presenters throughout the presentation, please do put them in the chat, and we'll get to them at the end of the presentation. With that, the floor is yours, Jamie. Looking forward to your talk.
Thank you. You can hear me all right, I assume?
Yes.
All right, great. Yeah, maybe I should have shortened up that intro, Charlie. They might know too much about me now, but I appreciate that. Yeah, at PNNL, I work a lot on DERs and context for this. I do focus on interoperability. I work a lot with standards. We're going to touch on a few of those standards, and we'll see how time permits. If I get through some of these slides, we'll, of course, leave plenty of time for questions and maybe touch on a couple of other activities that exist out there in industry. I apologize in advance for looking down to get the full screen. I had to use my laptop, so it's below my camera quite a bit here. So we're going to start out just kind of going over the topics we'll touch on, communication requirements, some functions that are required to enable communication, a little bit about scoping, and then the protocols themselves. So in clause 10, we really are talking primarily about protocols, but there's a lot of discussion about this thing called the local DER communication interface. This is a nuanced topic because there's interpretations of it, but we believe it should be a physical place where you can plug in something, right? So kind of funny little sidebar joke. Just because it says it's available, some people think that means that it can be a accessory card that sits on the shelf in a warehouse, and that is not the case. We're clarifying that in this round of revisions. It has to be a local port available on the DER to plug in your Ethernet, your serial cable, whatever communications port is defined for the project. But the idea here is that it allows information exchange requirements for all of the applicable functions in 1547. There could possibly be an additional communications port that the utility or a third party might use, like an aggregator. But this one is primarily for the use of the utility to make sure that they can do things like modify settings, validate curves, and so on. A lot of that functionality that Jeanette alluded to, I'm sure, earlier. So under mutual agreement, additional capabilities are allowed. So that means those additional ports that I talked about, those are allowed by mutual agreement. The utility may not want others to have access to those DER. And then whether or not that port gets used is up to the area EPS operator. So I know in a lot of interconnections, they're primarily using that to validate that the settings are set and then it doesn't have to be connected in real time. Although I think if I could make my recommendations, because we have such a dynamic systems constantly changing these days, we're using other things like flexible interconnection. It would be beneficial if this was a live port at all times connected to some sort of communications protocol, whether it's through HTCP or something like that. It would be helpful to have this port being used. We're also having conversations in 1547 about a gateway. And so being able to modify those settings does require that you have something plugged into it. So I would just consider that when you are deploying. It's up to the area EPS operator if they want to use it. If there's any operators in the room, it's probably better to be safe rather than sorry and have some future proofing there by using that port continuously. So the information that's exchanged over that local DER communication interface is nameplate data, configuration information, monitoring information, and then management information, which includes that update to functional modes and settings. And if you are in a utility where things are changing and you do have need to change those settings, better to avoid the truck roll and keep that communications interface plugged in. Some of the information that's going to be monitored: active power, reactive power, voltage, frequency, operational state of the DER. In context of 1547's base standard, the operational state of the DER is generalized. So you've already heard this. We are not device specific, definitely talking about agnostic. And 1547.9 touches on the energy storage side of things, and the operational state there could include the state of charge. But in 1547, it does not cover that. It's really looking at whether it's importing and so on, or sorry, whether it's exporting and so on, or whether it's offline. So not necessarily whether it's acting as a load or addressing any of those energy storage specific type of capabilities. Whether the device is power connected, so whether it's actually online and connected to the system, alarm statuses, and then operational state of charge. Now that's a tricky one. I'm not going to get into the weeds on operational state of charge. It does apply more to energy storage. So not specifically called out in the base standard, but it does mention that that is one of those attributes. And operational state of charge has a very specific definition associated with it. I'll let you reference .9 for the details, but essentially it's what's available to be used. Management information, of course, constant power factor mode parameters, voltage reactive power mode parameters. So these are all operating parameters. I'm not going to read through all of these, but some of those things that would possibly be changed would be things like droop parameters, right? And depending on how stiff your system is and so on, voltage active power mode parameters, all those things could require changes over time. And that's why I would usually recommend to my industry partners when I'm working with them that if you have an option to keep that port connected and be able to actually monitor these things in real time rather than just having to roll a truck and plug into it, it'll provide value, even if it's just monitoring, but definitely if you have to update those parameters. So I'm going to go over the scope of the interoperability requirements here pretty quick, but the key here is that it's really that local DER communication interface. I think you guys can probably see my cursor, but this little box right in here. So you may have network adapters, utilities, some call them gateways, that allows you to deal with the DER managing entity and so on. But the communications really is defined right here at the edge of the DER system. So on one side is the DER system, on the other side is whatever network equipment is connected to it, whether that's a stationary technician with a laptop standing there in place, plugged into it, or it's a gateway, or whatever it is. That is not really in scope. What is in scope is how that thing communicates with the DER plant, DER system on the other side. You'll notice that the DER system itself and what goes on inside is out of scope. And why that's important is because if you think about a DER system, you could have Sunspec Modbus operating locally, but it might not be just the 1547 requirements. It could be beyond that. It could be a subset of those. It could be proprietary stuff going on within the system. So if you've built an inverter, you have your own secret sauce within that inverter. That's not in scope, but that interface needs to support all of the 1547 interactions. The other way to look at this is like from a plant controller, right? So a plant controller would have that DER communication interface and that management associated with it for 1547. But behind it, it could use Modbus that's not at all associated with 1547. There's a list of eligible protocols. I've mentioned this a little bit already. You guys may have heard of SEP2, that's 2030.5, which just recently went through a revision. There is 1815.2. This is, well, let me step back. 2030.5, just for context, is primarily used either between the utility and aggregator or the utility and specific DER. So it's almost kind of bridging the utility to customer side, if you want to think about it like that. 1815 is DNP3. So that's probably the dominant communication protocol here in the United States. Specifically in 1547.1, there's a data model that's called out. It's important to note this because 1815 is one of these protocols, which is just kind of like registers, right? You just kind of put things in a register and read and write and read and write and read and write. Without having the semantics that you need associated with those points, voltage, for instance, or phase one voltage, to be more specific. You may have phase two voltage on a port, read it as phase one. So you need this semantic interoperability. 1815 by itself does not have that. What you'd be looking for is in 1547.1 called out as MESA DER. Now, MESA DER is really just the data model associated with DNP3. So it's a 61850 and IEC 61857 420 data model associated with 1815. Now we're just going through wrapping up the final commenting phase, and we expect that to be an official IEEE standard. So if you are looking at using DNP3, I highly recommend you put in your procurement language 1815.2. And all it says is that this is the data model associated with DNP3. So it just takes it one step further and defines some of the semantics associated with it, that analog point X is voltage, for example, voltage phase one. Okay, so we've covered 2030.5. That is the kind of customer to utility type interface or aggregator to utility type interface protocol. 1815, more of a utility SCADA communication protocol. And then Sunspec Modbus. Now, Sunspec Modbus is interesting because it's pretty much a site type protocol. So I'm going to just back up really quick here to this little diagram. And remember, I said there could be a gateway here, right? And so that would communicate via whatever the utility DER managing entity wants to the gateway. And then the gateway would be a local controller, and it could use Sunspec Modbus. Specifically in the most current version of 1547, this is the 700 series inverter data model that's called out. And it's not the entire model. And I've got another presentation that we can talk about some of the things that are left out of 1547, like energy storage. But specifically, there is a set in 1547.1 of the list of data objects that are mandatory and optional. So definitely suggest that as a companion to any 1547 protocol is any 1547 specification, you would also look at the .1, the test procedure, to make sure that you're getting all the right data objects that are defined. So here's an interesting one too. We've already covered a little bit, but the availability of communication. So when the DER is operational, it is required. Um, it may be active and responsive whenever the DER is operating, and a continuous operating region or mandatory operating region. But the real nuance here is whenever the DER is operating. So in the latest revision of 1547, we are discussing how we might change this language to the local DER interface is always available. Because just because the sun goes down, does that mean you shouldn't be able to communicate with your DER and change settings? There may be some instances where when the DER is actually not generating, that's probably the best time to change settings and to modify things. But if you can't communicate it because it's technically not operating, that can be problematic. We're also talking about this in context of EVs. Technically, in order to be a DER, the EV and EV charging station are both need to be co-located together. And if that means that there's no EV plugged in, is the DER operating? Well, I need to be ready for the next DER, so maybe I need to be available to change my settings before the EVs arrive and start doing their V to G thing if that occurs. So while it says in the current 2018 version that whenever it must be active and responsive whenever the DER is operating, this is one of those areas where you should make sure that when the new revision is complete in another year and a half or so, you confirm that that's still the case, because it may be that the DER's local communication interface is always supposed to be available. We'll see. The read and response time currently is less than or equal to 30 seconds. That's the maximum amount of time to read and respond to requests. I think that, as we go forward, these types of things may have benefit to be less than, but there is always going to be a maximum. Okay. So should I stop and answer any questions, Charlie or Rico, about comms before I go into cybersecurity?
I don't see any questions there now. Does anybody have any that they'd like to ask? You can throw it in the chat.
I know it's a dry topic, but I live and breathe it, so love to hear some questions.
I had one I was going to ask, but you already answered, which was required update rates.
Yeah.
Okay,
Right.
you're good to go.
One question, Jamie,
Yeah.
is interoperability was a new addition to 1547. Do you have any sense of the industry's response?
We have
Are they generally,
yeah.
are all inverters generally accommodating this and getting the UL listing, including the interoperability requirements?
Yeah, in if they are 1741 SB compliant, I should say conformant, sorry, then they should have met the requirements for interoperability with one of those three protocols. Commonly, that's SunSpec, just because I think primarily because it's easiest for them to implement. There is requirements in California under Rule 21 for 2030.5, but that's actually between the utility and the aggregator, if there is one, and typically there is, but if it's utility to aggregator or utility to DER, it's been mandated to use 2030.5. The fact is that jurisdictions are slow to adopt or verify things themselves, and sometimes that SB certification gets slipped on there without necessarily having been certified effectively, I would say. That's a caveat. So I see an uptick, but it is a challenge. And I think that's one of the most important things about procurement language is that, between policy and procurement languages, those are your accountability pieces, right? If you don't have anything defined in your procurement language and your jurisdiction doesn't have a regulatory policy, then you don't really have anything to hold them accountable to making sure that it is what they say it is. So that's really important. And that's about as far as I can go. I think it's getting better. I don't think it's perfect. And I would definitely like to hear others' comments based on their experience. That's just been my personal experience so far.
Thank you, Jamie.
All right. I don't see any other questions popping up in the chat. I got that up now. So let me know if you do, and I will continue on. Now, we have some real experts in the room. Jeanette Sandberg, I don't know if she's still here, but Jeanette is was the chair of 1547.3 2023. Congratulations to her on getting this through. This was, I know, a big lift. It's really valuable guidance. This is a guide, so nothing in here is necessarily a formal standard, but these are like best practices that you should certainly consider when trying to apply for cybersecure systems and making sure that your DER are cyber secure. So where it fits in the family of standards, you have the base standard, which is primarily what we cover. You have the testing and certification of .1. .2 is an application guide, and then .3 is the guide for cybersecurity. There's some more. The .4, you probably heard that's got an underway revision. .6 should be coming up shortly. .7 is ongoing. .9, Charlie Vartanian, who's on the call, did a great job with Mike Ropp and pushed that one through the finish line. And then .10 is currently underway. So you guys can see we're all busy working on standards. So anytime we get one that's within a couple years, we're really happy because that means we've got at least another year before we have to revise it. Cybersecurity essentially exists because 2018 really doesn't have any cybersecurity. It's got interoperability, and it just says, hey, think about cybersecurity because that provides low risk if you have cybersecurity addressed. The .3 material, some of it has been pulled into 2018, but really that was old, dated material. It was previously like an interoperability standard. So now it has been converted to where the .3 interoperability was pulled into the 2018 version as the interop stuff. And now we have this .3 has become just strictly cybersecurity. So it isn't included as a subclause in .2 because it is a guide, and .2 is an application guide for the base standard. So cybersecurity is also very jurisdictionally specific, right? So you're going to draw from your requirements within your organization. You're going to draw from best practices in the power systems community. You're going to draw from NIST and NERC and those kinds of entities. And it's pretty big, really. It's a big, you unpack cybersecurity, you're unpacking a big bundle. And, depending on what topics you're trying to address or what risks you have, you may be more or less strict on cybersecurity. This standard was co-sponsored. So there's a few standards in 1547 where they are kind of specific, more, and I don't want to say technology specific, but maybe discipline specific is a good way to put it. And so the topic of cybersecurity is also covered under Power Systems Committee. So the Power Systems Subcommittee has had a co-chair that they donated to the cause, and SC21 had a chair that they donated to the cause plus a co-chair. So I think actually I guess it'd be a vice chair, I think, too. So anyway, it was blended exercise between the two committees, and that's really important because there's a lot of expertise out there, and those who work on DER and DER integration have one area of expertise. The folks that are working on bigger, broader power systems have a broad area of expertise, and really this standard kind of gets at both, right? There's DERs involved, which are distributed resources, then there's also power systems operations, and you're bridging the two, right? So they split out into separate guidance for cybersecurity that's specific to DER, and that's how 1547.3 was kind of updated. When I went through the update, they pulled out the interop stuff that it was in the 2018 version, and just focused on cybersecurity in the new revision. So really, three main areas: why, the recommendations, and then how do you make sure that things are cyber secure? So testing and testing intervals. You'll notice that this is not a testing and testing intervals and that's associated with .1. This is above and beyond. So .1 is really related to the base standard and the requirements set forward in this. .3 still needed to have recommendations related to testing and making sure that things were secure. So there's also, besides the testing and certification recommendations, there's always this thing in 1547 standards where they say, hey, you know, this is really important for people to know. We don't want to overemphasize it or put undue requirements on those that may or may not adopt them in their entirety. We always want to have examples and things, and sometimes they just don't fit into the body of the document. So we put in annexes to cover examples. So like in 1547 revision, we're putting in an annex right now about V to G. It's a specific use case. We're being technology agnostic in the greater standard, but we want to make sure that there is some details to give people some guidance. So these annexes are on cloud computing, unique and new. And actually in 2013, I think this is pretty forward thinking. We're really just now getting out to the adoption of cloud computing. There's a questionnaire, which is kind of like a guidance on what kind of questions you should ask, and really beneficial to use things like that in your procurements. Did I ask the right questions? Did I make sure I covered all the cybersecurity risks? There's a lot of documentation out there already, and I agree with this comment here that NIST cybersecurity, they've got extensive cybersecurity documents for critical infrastructure and for DERs and for other things that are applicable, especially when you're bridging different types of communication, different protocols. And then there's also additional details on the protocols that have cybersecurity and those that don't, right? So DNP3, there's a layer of cybersecurity. There could be a recommendation to use secure authentication. And at the time it was version 5, now it's version 6 under revision. But really those don't necessarily inherently have security on DNP3 and on Sunspec. That's a layer. And then with 1547, it calls out those two plus 2030.5, where 2030.5 has security keys, what they call PKI keys, so public key infrastructure, where you can validate the security, and it's part of the standard, right? It's part of the communications and happens consistently and routinely in a very defined way. So there's this risk assessment that's in there, and a lot of this kind of 1547.3 in general, right? There's a lot of documents out there, but it puts all of these kind of key best practices into one place. And so, you know, it's always going to give you should look through the biblio and make sure that you're looking at the other documents like the cybersecurity framework, risk management framework, and so on. And all of these standards have some risk assessments associated with them. And basically you're gonna not get, you know, a defined, since it's not a formal standard, it's a guide. You're not going to get a defined process for exactly how you do it. You're going to get guidance, right? And so this is really important to look at both .3 and what those risk assessments they have identified, but then also in your jurisdiction, whether you're running operations at the utility or you're an aggregator, you definitely are going to have unique things that you need to assess risk at. This clause that they have addresses generally the risk assessment and management of anything associated with DER, but it also talks about this cross-organizational piece. So not only talking about where you go to look at the right kinds of assessments for your environment, but some of those things that might be unique because you are crossing boundaries. You are working with utilities, aggregators, and resources, right? I see a comment in here. I'm not sure I get the Rule 21 comment. I think that's on my last slide, so I'll go back to that one. But does the cybersecurity standard address intrusion detection and monitoring? That's interesting. I actually don't think it does. It's not a standard, it's a recommended practice. So it would give you intrusion detection and monitoring documents as references, but I don't believe it actually does go over intrusion monitoring itself. So it does have these best practices. I would say that NIST cybersecurity framework is one of those that does give intrusion detection and monitoring best practices. You're going to be looking at, in this case, more of the highest level guidance that you could get as a cybersecurity analyst. And I hope that answers your question. If not, we can also call on Jeanette, who is intimately familiar with .3. So
Jamie, were you going to back up a slide where Rule 21 was referred to?
That's in the interop clause. I can go back to that. So when I mentioned Rule 21, I was mentioning the 2030.5, but perhaps Kep, I hope that's your name and not initials. Do you want to either clarify in the chat or verbally your question? Yeah, I think I'll look for it in the comments unless Kep's coming on.
And Jamie, I'm going to add one more general observation for the group. Rule 21 is California's retail tariff for distributed generation or DER interconnection. This is a great example where it points to or references 1547 2018. So in general, it's going to default to that for all the clauses. It doesn't cherry pick. Other jurisdictions will go in and be very specific on what clauses they call out. The other good example to call out here is sometimes jurisdictions add requirements above and beyond 1547. They're not that's not in conflict with 1547. A classic one is Rule 21 adds the need for a lockable disconnect switch. That's not in 1547, but that jurisdiction will call for a mechanical, lockable, visible disconnect switch. I wanted to share that thought. So even though PUC may refer to 1547, that doesn't stop them from adding additional requirements.
Yeah.
I'm going to put it for the end, but I am curious on NERC SIP relative to all this, but we'll hit that later.
Yeah, and to add to the Rule 21 comment, for example, I think one of the best examples I can find is where 1547 just says you have to use one of three protocols. Rule 21 says between a utility and an aggregator, you must use 2030.5 default as the default. By mutual agreement, you can use something else, but the default for Rule 21 is 2030.5. The other one to point out too that's kind of like that is Hawaii's Rule 14. So good notes to have in your back pocket if you're working in either of those states, or if you're looking for some states that have mandated 1547 requirements. If Alaska hasn't done it yet, maybe they can look to those as some references and guidance as to how they did it. Okay, so back to cybersecurity. So we left off here. And like I said, one of the benefits of .3 is it talks about this cross-organizational risk assessment, and that's not necessarily covered specifically in some of these other documents, but you're going to use pieces of both of multiple documents. All right. So clause 5 consists of both general and specific recommendations. So examples are unique username and password. So don't leave password as password. That's probably your number one risk. If you leave a DER, the local communication interface is accessible and open to anybody that wants to come and plug into it. Having your default name as username and your default password as password is very unsecure. And so if you look at that during commissioning and make that modification, you also want to make sure you have that somewhere where the future users can get it, because the last thing you want is a technician to set that and then you not be able to access the DER ever. User-created passwords follow a set of rules that are adhered to. I think this is a really interesting piece that we all know and love. Anytime we go and log in to Amazon or PetSmart or wherever you're shopping, this has kind of become the norm, right? So we think some of this is really obvious because we deal with it in our day-to-day lives, but the fact is that people just kind of go as fast as they can sometimes. And so making sure that we're doing these simple tasks during commissioning protect things and make them much more secure. And if you don't do it, you're at risk. Your electrical system is at risk. Your DER is at risk. Potentially your market participation is at risk, and so on. So network engineering, I don't know how many network engineers we have on the phone, so I'll kind of cruise through this. But there is a what I work in is grid architecture, and a big portion of that is networking and how we communicate and exchange data. So you have your communication network and the types of protocols, the interactions between DERs and those protocols, the physical and logical topology, so how you segment a network, where your firewalls exist, and so on. Where you have a DERMS versus your ADMS, or your SCADA system, right? Those boundaries need to be clearly defined. If you don't define them, you put yourself at risk, and you'll hopefully catch that in your thorough risk assessment that I'm sure you all are going to do. But really, you're trying to basically be proactive and building in defensive posture. The reality is that the small tasks make things hard for others, and those that have not completed those small tasks are the first to be at risk, right? You'll evade one jurisdiction because they do something that makes it harder for another jurisdiction where it make it easy because they didn't change the password from password. This segmentation is also between the resources on the network. So whether that's substations, feeders, whatever, whether it's between the aggregators and so on, or within an aggregator, between certain areas within their network, and so on. All of this is kind of, if you're cybersecurity 101, if you're a network person, but power system people, or, hey, we had air gaps for 100 years. So that was cyber secure, right? Air gaps were all you needed. Now we're not dealing with air gap systems. They all have a local communication interface. So anyway, this clear separation piece between systems and architectures is one piece. The last piece of this is like role-based access control. Who is going to manage the equipment, right? So if I have the role of being the DER owner and operator, and another role is the utility, and another role is the aggregator, that's just 3 roles. What if there's another participant or another actor in the system? What if it's an OEM that wants to do updates? So you do have to have different levels of trust built into both the devices and the network. And you also need to be able to manage that continuously, right? So we want to make sure that as roles change, the system also changes, and you adjust the roles accordingly. And that does include removing roles. You don't just want to add people to access and be able to access and give them permission arbitrarily. And you may want to, and you occasionally want to review all of the roles and make sure that those who do not need access also have that access removed. So my personal preference is that the first 3 things, that if you went and read this like a book, those first 3 things, those are kind of typical processes when you're setting up something. But that last one is really a continuous activity. You need to make sure that those roles, those are very important to define and revisit very routinely. Okay, and this is about access control, which is great. We rolled right on from that conversation to this one. So yeah, the section refers to the best practices, keeping humans out, right? So back to what we said, access control recommendations, who should have access to what, so you don't have to necessarily come up with those roles yourself. And also, these are not going to be always the same. Different entities and different actors are going to require different levels of access control in different jurisdictions. There's some general access recommendations. You should never give access of somebody to change those settings unless they're authorized, i.e. the utility or owner. And then the other pieces like system access recommendations and management access recommendations, all those end up being roles, right? So there's a whole section on what kind of access individuals need, what kind of access systems need, and then the big one that I mentioned already is role-based access control. All right. Data security recommendations. So utilities continuously managed. Yes, cybersecurity. Yep, that's right, Charlie. So this comment from Charlie that's in there. It's cybersecurity changes, the need for updates always changes. So it's a recommended practice. Currently, someday it could be a standard, but I think what ends up happening is specific requirements end up probably getting elevated to the base standard at some point, and we're already looking at some of those things. And then, yeah, all of these things become a process, right? So you put them into your business practice as every 3 months, or in case of some notification, whether it's a vendor maybe identifies a risk associated with one of their products, right? So it's a combination of you need to have a routine in place as an industry entity or stakeholder. You have a routine in place to go through these processes, but then also you have to be out there monitoring what actually is happening in the world. Heaven forbid we could all afford to have our own cybersecurity analysts on our team and game the system, see if we can hack in and so on. It's not very likely. So the best we can really do is just make sure we have schedules in place to do these assessments, and then also make sure that we're aware of any industry changes or risks, and whether it's a product or an exploit that's identified out there. You definitely need to make sure that you're doing this on a routine process at all times. As soon as possible, you need to identify these things. Anytime that you haven't adapted or I guess made accommodations or restrictions based on what's going on in the world, you're at risk for that time. And if the others are more proactive than you, your system is even more at risk, because any hacker or bad actor is going to go for the simplest intrusion that first. That's just how it works. Okay, so the data security recommendations is this is pretty critical, because regardless of security, you're only as strong as your weakest link, right? And in this system that you have with DERs involved and this bridging between actors, I mean, there's financial data, there's environmental data, so topology potentially, there's potentially passwords and things like that, right? And so wherever data is stored, it needs to be protected. And again, kind of the same things apply to the network, segmenting your data. Some data might be transmitted, it might be required. 2030.5, you have to communicate with using keys and so on. And so, you have to transmit some data, and you don't want to disclose that to bad actors. So you need to make sure that any data is segmented. And then there's data from power system operations, right? So, there's a joke a few years back, or maybe it wasn't a joke, but somebody said, well, you could destroy an electrical grid just by hacking every thermostat. Well, I don't know that that's practical for a hacker, but think about if you have a 200 kilowatt DER on a system, the damage that you could potentially do by knowing what the status is of that DER, right? If you know it's on or it's off, that gives you some insights into that network, that power network, that energy network, that you could potentially wreak havoc with by turning off a different DER or turning on a different DER or any other thing, any number of things. But that data that you transmitted or didn't transmit, whether it's personally identifiable information or power system data, that has risks associated with it. And some of it is definitely causes more risk than necessary. Some data needs to not be stored. Some data should be purged, but doesn't get purged, because we all think data has value now, right? So we build up these big databases, but that could be risky too. So at some point, maybe you need to consider purging your data. Anyway, data security recommendations is really important in .3 as well, and needs to be considered. And then this goes back to this security management recommendations. And I covered most of this, but I think there's a couple of things here that I'll touch on that are really important and kind of topical currently. So I work at a national lab. I think we're pretty cool. We do a lot of cool stuff proactively with cybersecurity and so on. And so it's always interesting to hear tales. And then Charlie and I even hosted a couple of safety and reliability forums. And so on this topic in here, we talked about general lifecycle management and patch management, and event logging, to go back to the monitoring piece, right? Backups, and operating system applications. But one that I think is really interesting on this topic is supply chain management. And so we're doing studies at the national labs, and we're finding actually there are significant risks in technology. And it's not really things that you would know about, right? Could be communicating over networks that you do not even know exists. Think of like Apple AirTag communicates over existing cellular network. Anywhere there's a cell phone, that AirTag can communicate over it, whether it's on that, whether it's able to access your phone or not, it's using your network. And so supply chain management's become really a hot topic. So think about when you buy an energy storage system and it's made of a bunch of different components. It's got inverters, it's got battery management systems, it's got meters, it's got the energy storage itself, the batteries, right? The modules, the racks, the controllers for each rack. And so there's, maybe 100 parts, any given energy storage system. Any one of those pieces of hardware could pose a risk. And so there are now certifications. I can't remember what the acronym is, but I think it's TTS or something like that. There's a standard that you can, when you buy equipment, you can know where it was made, and it's been verified that it doesn't have a communication capability or an ability to be breached. So what happens is if you have a battery management system and you have like a meter in the battery system, if that thing was made by a malicious actor, they could phone home, and they don't necessarily have to use the communications of the network that it's installed on, right? It could be using some sort of wireless signal, and other things that you may not inspect. So this piece of supply chain management has become a really hot topic. We're trying to buy equipment that has reputable vendors, and it's not just the person that manufactured the equipment. It's from when it was manufactured all the way down to when it was installed. There is risk associated anywhere along that supply chain that they could be modifying the equipment or otherwise maliciously acting. So supply chain management is really important. And I'll leave it at that. We covered the other things. So here it goes back to the monitoring and coping. Now, I didn't actually realize this. I apologize, but it does say recovering from security event. So who do you call? I guess that's a good thing to know. I'm not sure who you call, right? What piece had a security event, and I think that this is really best practices. So right down there at the bottom, I think that's the big kicker is you should be reading those best practices. And I personally, have read the NIST cybersecurity framework. Believe it or not, I actually have read one of these documents all the way through from beginning to end, better than I did the slide deck, in fact. The NIST cybersecurity framework does have these recommendations. And depending on your industry, this document may not cover what you need to. So not only do you need to know how to answer these questions, you need to identify the best practices and have those in place beforehand. So again, going to those documents, that this best practice, this guide, will give you a list of all these great documents that will help you build these plans. And that, I think, is the most important part of any of these things, is just to know that you need to ask questions. That's one thing, but then you need to have plans in place so that if something does happen, you can address it, or proactively, hopefully, because hopefully nothing will ever happen negative, right? Proactively, you can address these concerns. So following the guidance from other documents is just as important as going through this, which will give you a high level of cybersecurity. And then this is the annex that we mentioned earlier with the questionnaire, which I also think this is great because this helps you build those plans, right? What security standards do you follow? What is your target maturity level? And we do this with interoperability as well. What's your maturity level? Is there a group that you can ask questions of that will help you identify the risks ahead of time, right? So being proactive means you're at a higher maturity level than if you just do it once and forget about it, right? What are the purposes of the systems? What are you connecting it to? What's upstream? What's downstream? It's not just about the system that you're directly assessing. It's also about the other things that are interacting with that system. What's the network topology? How could you isolate, segment, secure the system? What do you do in case there is an issue? And then digital and physical assets, which are important to maintaining your security and integration of your integration and systems. And I think this is really interesting too, because this actually is, we have a lot of digital things, keys and security things and so on, but firewalls are a physical thing. They sit at a box somewhere, and are they getting updated, right? So we need to make sure that we're both identifying them and how we're maintaining them, and updating them and addressing new concerns as they arrive. And then access control, of course, incident management practices, and that's probably the key. I would say each jurisdiction is different, and you need to have very specific incident management practices to your jurisdiction. All right. Testing and commissioning. Now, this one's interesting because, again, this is a guide. So the testing and commissioning is going to be guidance. It's not going to give you strict tests, but it does give you objective means, like what kind of questions you would ask, right? How you would test it, is probably less prescribed than described, right? So they're going to talk about means for evaluating cybersecurity controls, identifying weaknesses and vulnerabilities, gaming, and so on. Always good. Hire a hacker, see if you can get in. Also means for evaluating the posture of the target system, right? Are you proactive? Are you lackadaisical? Do you just deal with it when it comes up? Do you have mandates in your state? So on. And then the life cycle of a device, right? So we're talking about manufacturing, commissioning, deployment, supply chain, so on comes into that area. Testing and recommendations for individual DER, but that's again not just what we're looking at. We're also looking at the networks they reside in. So testing your firewalls, making sure those settings are correct. Every time you add a DER, you may need to do that same assessment, or you may set it not once, right? We're not setting anything once, but you may set it over a calendar period. You may do those modifications. And then this is kind of a risk mitigation activity, right? This is not foolproof. So you need to it needs to be integrated all with your overall risk management, including updates and assessments that happen continuously. And then we'll go to the next slide, where there's a representation of roles. And I'm not going to talk through this slide. You have a lot of experts, I'm sure, in your organizations that deal with this far better than I do. I would just say that this is a good example, not a conclusive or jurisdictionally specific example. It is just an example. So you do want to note that you have a testing entity, you have a vendor. I think that the one that it is becoming more and more prevalent, and we are dealing with routinely now with 2030.5 and so on, is the registration certificate authority. Who do you ask if you can have permission? How do you get permission? How certificates get approved? What's the life cycle of certificate? That's all really important. There's a maintainer. There's also an area and maintainer could be like an OEM potentially. It could be a vendor, could be the installer. Again, a general description of the actors, and then where they fit in, right? So I think you're going to see here. There's certification testing. I honestly think that happens at some point with everybody involved, right? Because it's also the people that are procuring it need to understand certifications and so on. You have design tests, production tests, and then look at all these people in commissioning and post modification and routine testing. Like you have to have a list of these stakeholders. They have to understand the roles. The roles have to be well defined. Again, this is an example. It's not conclusive, but I think it's important to understand that there are multiple actors involved in this periodic assessment. It's not just something that one entity does. It's usually teams of folks from multiple entities. All right, testing areas of focus. Talks about the purpose, the audiences, the pre-installation, and then continuous improvement. I think organizational continuous improvement, that is really a maturity of your entire cybersecurity processes. So we talked a little bit about that before, but I can't emphasize enough, you need to be always up to date, monitoring what's going on in industry, and also looking at what the best practices are, what vulnerabilities have been identified. So this is a ongoing thing that you need to be taken care of. And then risk management, those assessments happen routinely. I think we've gone through most of this, but needless to say, it's as on-site testing. So you'll need to get all those organizations involved, right? Including those parties that might not, on-site might not be the best term to use. So in-service is probably better because you are going to be doing cross-organizational testing and validation. And then you're also going to be assigning roles with any of these DERs. So this cross-organizational requires agreements, right? Who does what? Who's responsible for what? Logging, backups, how long are those kept? Making sure that those backups actually are collecting all the data they need, and so on. And then, of course, the periodic testing that we already have talked about. Right. So this topic here is the one that's nearest and dearest to my heart. I love cybersecurity, but it's not nearly as exciting as commissioning DERs. So the idea is that interoperability is not, it's not a one and done. There's no one protocol solution. There's not one test that says you are interoperable, period. You will work with anything. Now, we even have this today in our cell phones where you download an app. You have computers where you can just plug in a printer and print things. We have some level of interoperability. We don't get there just haphazardly. It didn't just happen. It's a lot of work. There's a lot of tests and certifications. There's a lot of stakeholders like ourselves that are working on these problems. And there's a lot of systems that have to be tested. So end-to-end interoperability is a challenge too. And then, of course, there's cybersecurity, which is very complex, as you now know. So we've got in the grid, this is the grid, so it says GMLC. This is the GMLC interoperability model, which is based off of the Gridwise Architecture Council's work, which I'm the admin for. They've identified 7 categories of interoperability. And what we've got is really, it's called the GWAC stack. But there's all these different things that really support each other. So the technical, you've got protocols and communications, and you've got informational, which is kind of like semantics. You've got organization, how the data gets organized, and so on. Operations and performance, self-explanatory, safety and security. And then you've got configuration and evolution. And we've talked a lot about how things change over time. And in order to be mature, you have to be constantly giving your best practices and your experiences back to the community. Them existing in your own little organization doesn't help the overall system mature. Therefore, in the future, when you go to do something else, you are going to have to do that all yourself unless you've shared your lessons learned. So the category of community is actually the most important. That's why it's big, right? Out of this interoperability maturity model, we built 33 total criteria. 10 of them are really about feeding back all your experiences into the community, developing standards, best practices, documentation, lessons learned, all those things. That all requires community. So with all of these communities, the best part of IEEE, since we're doing this with a bunch of IEEE folks, best part of IEEE is great community, right? We've got the people working on the formal standards. We got people working out on the guides and so on, trying to feed back all this community information. So I'm going to go through a couple of things right now just on the protocols. We've got the DNP3 protocol, which I mentioned. So there's an application note out there that gives you semantics. Very important to have the semantics. And then in .1, it calls out the application note specifically, but going forward, we're going to have 1815.2. So your new buzzword, instead of saying DNP3, 1815.2 is a formal IEEE standard that has semantics associated with it. Very important to being interoperable. We've talked enough about 2030.5, but I will just mention that it's more of an IoT protocol. It has security built in. Sunspec Modbus is really device level. And I want to note again that it's very important that 700 series inverter model be used because it used to be a 100 series model. All right, now we're getting into the fun stuff. So in the testing and certification component, we have different categories of testing. You have communications protocol testing that bits on the wire, and then you have functional testing, meaning that if something was told that it needed to ramp up or down, it needed more real or reactive power, whatever, did it actually do what it said? And then you have system testing, which is usually done on site, factory acceptance testing, as built testing. And that just means that all the components worked together as they were supposed to. So we have some potential for gaps here. And I'm going to cruise through this pretty quick because I know I'm running out of time, but it's really important to know that 1547 and 1741. 1741 is a certification for 1547 based off the .1 test procedure, but that does not cover everything. And so you have these other certifications that SunSpec or Mesa could provide. So you have these models on the bottom. They're all different components of an energy storage system, 700, 800, and 200 series. One's the modules, one's the inverter, and so on. When you get to an energy storage system, communication comes in from the top, from the utility, gets, special sauce in the middle of the control system, and then all the other devices contribute information and are controlled by that main platform. This is where the stacking of testing and certification comes in. It's really important that you think about what 1547 covers, ride through, volt watt function, continuous VARs, power factor correction, those types of things, right? Well, it's not power factor correction, it's constant VARs, fixed power factor correction. Those exist in 1547. Those are what gets tested. But look at all these things on the right side. These are the energy storage capabilities that are not in 1547. Frequency watt curves, power factor correction functions. So when power factor is off, it steers. Pricing, scheduling. Scheduling isn't even included in 1547. And then there's some active power like the generation following. Those things are really valuable if you're operating one of these storage systems. Those are the key things you want. If your system has only been certified to 1547, you've missed all those functions on the right. And so you have other test programs that you want to stack. So you do 1547 testing and certification, that gets you part of the way. And then you do the Mesa profile, the communication protocol testing, and that gets you part of the way further. So it gets you the communications associated with storage. And then you go out and you do lab testing for functionality. They check and make sure, using some quality logic test tools in this example, that they are able to meet some of those other functional capabilities. The ones we're working on right now are those functional capabilities for storage. And so, in the final stage, you have factory acceptance testing. Just so you know, if you don't define factory acceptance testing in your procurement language, you miss a lot of these other things, because the factory acceptance testing or site testing that a vendor is going to do is going to be minimum. And if you want to make sure that they meet all of your requirements, you have to specify the factory acceptance testing. And not only do you have to specify it, but I would suggest that you use you actually validate and do your own acceptance testing before you sign on the dotted line. And I know it's hard to do if you don't have the technicians and specialists, but it's worthwhile investment to have a third party if you can't afford to do it yourself. And I'm going to skip through this. I think we can leave that alone. Basically, the Gridwise Architecture Council led to some of that interoperability maturity stuff. And I think the important piece here is that there is a decision makers checklist that has been updated. So let's see, right there. It's the one that's in like dark green, 2020. That checklist gives decision makers a list of questions that they can ask to make sure that they are buying interoperable systems. We have a whole bunch of great videos online from people like Xcel Energy and different vendors, all kinds of different great videos in that QR code, which is in the slides that you'll have shared with you. And I think we'll end it there. I'm going to leave that up so you guys can scan it while I answer Charlie's questions. So Charlie put a link in there for the gridwiseac.org. It also has links on that website for the YouTube channel. And the percentage of utilities that are using DNP as their COM protocol, it's a lot. I mean, it's most utilities in the United States are using DNP3. What I would say is they are not using Mesa. They are basically using DNP3 since it came out. and, air gap systems and all that, right? That's what we had in the past. And they've built their own information models as they've added things, they add new data points. And so the challenge is, Charlie, that it's ad hoc currently. And adoption of Mesa has grown, especially since people are procuring energy storage and they want to, be able to upgrade or add or whatever without necessarily changing their data models all the time or paying the costs associated with the vendor building a specific data model that's just for their system. If that vendor has to build you your own data model and map it to your system, that's many, many hours of work. If you use Mesa and you call out Mesa or DNP 1815.2, remember 1815.2. I wished I had a little bouncy ball and some text on the screen. 1815.2, that is the one that has the data model associated with it. It's so important to have that semantic model. So important. That saves a lot of money, a lot of integration costs, and most of the money spent on systems, energy storage systems, is integration. No, actually, I don't see MQTT in any of the documents. Although 2030.5 is a RESTful architecture, and it kind of works like a pub sub mechanism. Yeah, if you are interested, Amy, in participating and bringing up those kinds of insights, please join the working groups and let everybody know what you think. And if it's not a working group with IEEE, there are a lot of alliances out there that would benefit from hearing what you have to say. So Mesa is one of those. The SunSpec Alliance manages 2030.5, so you can learn more from those organizations. So yeah, love to see you in those calls. We're always looking for people to support.
Well, thank you, Jamie. That was a lot of information shared efficiently. Thank you. Let's hand the mic over to Mari, who will close out today.
All right, great. Thank you very much, Jamie. I want to thank actually all of our presenters today, starting with Mark and then Charlie and Jeanette and Jamie. I think we learned a lot about, the changes to 1547 as well as cybersecurity and interoperability, which I didn't know. So I'm actually very interested to hear that as well. We appreciate all the presenters and virtual attendees. Thank you, attendees, for attending, spending all morning with us. Tomorrow, we're going to look at broader issues, including other complementary industry efforts to promote the adoption of newer grid technologies, including grid-forming inverters, and leveraging the advanced performance features of IBR. If you learned anything new today, we encourage your friends and colleagues to join us tomorrow. And then it's always recorded if people want to go back and if they missed a day. Up on the screen, you can see what we will be covering tomorrow. And again, thank you all for joining us for the first day of the IEEE 1547 Interconnection Standard Enabler for Technical Innovation and End User Benefit Virtual Workshop. Thank you all very much.